So we had mentioned previously the idea of mass number, which we give the symbol A. And the mass number is equal to the number of neutrons plus the number of protons. And as protons have a mass of about 1 AMU, and neutrons also have a mass of about 1 AMU, then this makes sense that the mass number is approximately the mass of our atom in AMU. So if my atom is comprised of 5 protons and 6 neutrons, then its mass number will be 5 plus 6, 11, and the mass will be approximately 11 AMU, because this is going to be 5 times 1 AMU for the protons plus 6 times 1 AMU for the neutrons. Okay, so then we're going to kind of explore this concept of atomic mass a little bit further, and we're also going to look at the idea of what an isotope is and also what an allotrope is. So we've mentioned previously that mass and atomic number of an element can be illustrated using the complete chemical symbol notation, where we write the mass number above the atomic number followed by the element's symbol. So here is an atom of hydrogen. It has a total of 2 particles in its nucleus. So it's got 2 particles in the nucleus. That's the mass number. The mass number is simply the number of particles that are in the nucleus. And then one of those particles is a proton. This guy has 7 particles in the nucleus, what we call nucleons, 7 nucleons. And of those 7, 3 are protons. Now, because the number of protons always equals the number of electrons, we also know that this particular atom has 3 electrons. We also know that this is a lithium atom because we've got the symbol there. Okay, so that's kind of review in a sense. We're just elaborating on it a little bit. Now, this is interesting. We know that neutrons have no electrical charge. And it turns out that for a given element, for a given type of atom, that is an atom with a specific atomic number, the number of neutrons may vary. And this is very interesting. So if I have a carbon atom, it'll always have atomic number 6, but the mass number can vary. So atoms that have the same atomic number, the same number of protons, but they have different numbers of neutrons, therefore they have a different mass number, these are called isotopes. So isotopes always have the same atomic number, but they have different mass number. So for example, there are 3 isotopes of hydrogen. All of them have 1 proton in the nucleus, but they have different numbers of neutrons. This guy has 0 neutrons. This guy has 1 neutron, and this guy has 2 neutrons. But they are all isotopes of hydrogen. They are all examples of hydrogen atoms. So it turns out that most elements occur as a mixture of isotopes, and that mixture, the isotopes in that mixture are in a characteristic proportion. This is referred to as the percent abundance of each isotope. So the percent abundance reflects the characteristic ratio that the isotopes are always found in a naturally occurring sample of the element. So boron is a good example of this. It has 2 isotopes, one with a mass number of 10 and the other with a mass number of 11, and they're in about an 80-20 mix. Often we'll find that one isotope is found in much greater abundance than another, and we'll see an example later on of silver where there's 2 isotopes and there's approximately a 50-50 mix of both. So there's a wide range of these proportions. Most elements though have more than 1 stable isotope. Tin has the most with 10 stable isotopes. There are a bunch though that do have only the 1 isotope, but most of them have more than one. So now we're going to kind of start exploring the concept of atomic mass a little further. You can see that it gets complicated because in a natural sample of an element, there are going to be atoms present with different masses. So in that sample of boron, we had boron 10 and boron 11. You know, what does an average atom of boron weigh when we've got a mixture of the two isotopes? That's interesting. So we need to recognize, first of all, that the particles that make up atoms, neutrons, protons, electrons, have very small masses, and as a result, the mass of a single atom itself is very, very small. So this makes grams an awkward measurement to use when we're talking about things as small as atoms. So to get around this problem, chemists invented what we call a relative mass scale, based on what we call the atomic mass unit. And we mentioned this previously. And in atomic mass units, or what we call AMU, protons and neutrons have a mass of about 1, and electrons have negligible mass. Now, an AMU is very small, 1.67 by 10 to the minus 24 grams. So where does this scale come from and how does it work? So what we did was we said that the atom of carbon that has 12 particles in its nucleus, so that means it's got 6 neutrons and 6 protons in its nucleus, has a mass of exactly 12 AMU. And then we're able to assign the mass of any other object or any other atom as either a multiple or a fraction of that number. So 1 AMU is quite simply 1/12 the mass of a carbon-12 atom. And you can see I'm using that alternate way of identifying an isotope here. So what's in the periodic table are average atomic masses that are weighted for all of the different isotopes that are present in a natural sample. So you can see I've got 2 isotopes for boron. Boron 10 has a mass, not surprisingly, around 10 AMU, and boron 11 has a mass of around about 11 AMU. Now, boron 10 makes up about 20% of the atoms that are in a natural sample of boron, and boron 11 makes up about 80% of the atoms that are in a natural sample of boron. So what I would be expecting is that the mass on average for a boron atom is going to be less than 11 but greater than 10, because it's mostly 11 with a little bit of 10. So maybe it's going to be like 10.8 AMU on average. Now that's just eyeballing it, and that's not what we want to do. So what we want to do is to be able to calculate the average mass of a boron atom, taking into account the different percent natural abundances of each isotope. And this is how we do it for any set of isotopes for an element. What we're going to do is say that the average mass is equal to the percent of the isotope divided by 100, let's say we've got percent of isotope A, times by the mass of isotope A, and then, and remember we could have to do this up to 10 times, for every other isotope you're going to do the same thing and you're going to add all of those together. So the percent of isotope B over 100 times by the mass of isotope B, and so on for as many isotopes as you have. So here I have done this for boron. Okay, so it's the mass of the isotope with mass number of 10 multiplied by its percent abundance divided by 100 plus the mass of isotope B, that's the one with mass number 11, multiplied by its percent abundance divided by 100. And Sure enough, it comes out to be 10.811 AMU, which is the number that's reported in the periodic table. So the number that's reported in the periodic table is the average atomic mass. And it's a weighted average taking into account that the percent abundances of the different isotopes vary. So it is not a simple average. And if you just added the two masses together and divided by 2 and took the simple average, you'd get 10.5, wouldn't you? And you would be incorrect. So you can't just take the simple average. You do have to take into account the percentages of each type of isotope. So let's have a look at another one. So there are two naturally occurring isotopes of lithium, lithium-6 and lithium-7. Using the data below, calculate the average atomic mass of lithium. So let's just kind of look at it. This guy's going to be around about 7 AMU. This guy's going to have a mass around about 6 AMU, which is true. We can see that right there. It looks like it's mostly the 7 with a little bit of the 6. So I'm thinking that the mass is going to be a little less than 7. Maybe it's going to be like 6.9 AMU, something like that, right? Okay. So now let's do the math. We're going to take the abundance, divide by 100, times by the mass. And we do that for the second isotope. We're going to take the abundance, divide by 100, times by the mass. When I do that, let's quickly do the calculation now. What do I get? Sure enough, 6.94 AMU. Okay, so that's it. You know, that's how we do it. We take the percent abundance, divide by 100, times by the mass. We do that for every isotope and add them together, and that gives us our weighted average. Okay, we can do one more. I talked about this one earlier. It says we've got two naturally occurring isotopes of silver, silver 107 with that mass and this abundance, and silver 109 with this mass and abundance. So let's draw a little number line here. We've got 107 here, we got 109 there, and it's like 51.5% of that guy and 49.5% that guy. So if it was 50-50, it'd be 108, but it's a little closer to 107. So I'm thinking it's gonna be, you know, like 107.9 AMU. So that's my eyeballing it. 107.9 AMU, something like that. All right. Okay. Now let's do the math properly. It's always good to eyeball it first of all, and then you know if you've made an error or not when you get your final answer. So we've got to do percent abundance of the first isotope divided by 100 times by its mass plus percent abundance of the second one times by its mass, and we're going to get our answer. Here we go. What do we get? And I decided that it was, you won't believe it, 107.87 AMU, which was really close to what I decided earlier on. So just spending, you know, even if you don't do it perfectly, spending a moment or two eyeballing it really adds confidence that you've got the right answer. And of course, you can always check it against the periodic table. Okay, so a question that comes up is how do they determine the mass of these atoms to begin with and the mass of these different isotopes? There's a couple of different ways. One is called time of flight. So the TOF stands for time of flight. Mass spectrometry. So MS just means mass spectrometry. So you put your sample in containing your different atoms, and what you do is you ionize them. You knock out an electron. So you take your atom and you knock out an electron, and it's lost a negative charge. So a negative charge gets lost, which means that this guy now has a positive charge, and then that means that it'll be attracted to negative things. And so what we do is it comes through this slot here. So here our atoms come, it gets a beam here. At this point, you know, these guys have got a positive charge on them, and they are going to be repelled by positive things. So what we're going to do, let's put this around the other way, they are going to be attracted towards negative things and repelled by positive things. So if we put charges on these plates, they're going to come in here and they're basically going to get a push that way. And what will happen is they will separate according to mass. The heavy things will take a long time to travel down to the detector, and the light things will take only a short period of time. And if we have a standard in there, i.e. we have like carbon 12, right, then we can determine the relative mass of these different particles. So that's basically one way. Now, when you think about a car race, right, when we have the Indianapolis 500, it's a 500-mile long car race. So we don't have a straight track, do we? Because that would just be too big. So the accuracy of this measurement is dependent on how long they fly for. And so after a while, you know, this instrument gets very, very, very big. But just like the Indianapolis 500, rather than just having a straight path, what we can do is we can make the cars, or we can make our ions go in circles. So what we do is a similar activity, but we make our ions, our charged particles, travel on a curve. And then just like vehicles, you know, if you've got a big truck, it doesn't make the curve as easily as if you've got a little light zippy motorbike. So what happens is when we send these particles along a curved path, which we're doing to save space, or maybe we can even get them to go around in circles quite a bit, then they're going to separate according to mass, because it's easier to get the lighter ones to curve than what it is to get the heavier ones to curve. So that's another way that they do this. This is called magnetic sector mass spectrometry. So we really only have one thing left to talk about in this chapter, and that's the concept of an allotrope. And an allotrope is a form of an element that is not sort of like commonly found. So commonly, oxygen is found as diatomic molecules, and we just call this oxygen, or sometimes we will call it dioxygen. However, you've probably heard about ozone. And ozone is a form of oxygen that is not the most dominant elemental form. It's found at the top of our atmosphere, and it's comprised of 3 oxygen atoms bound together. So O2 and O3 are examples of allotropes. They are different forms of the same element. What we find is that there is one most common allotrope, which is O2, and then elements might have less common allotropes, such as O3. So for example, if we look at diamond, the most common allotrope of diamond is graphite, the stuff you find in pencils. But there is another allotrope of diamond, and that's referred to as diamond. And there are 2 forms of the same element. This one is common and is what we generally mean when we talk about elemental carbon, and this one is rare, which is why it costs so much money. Now it turns out that there's a bunch of allotropes of carbon. There are some that are C60, C70, really, really big molecules composed of large numbers of carbon atoms. There's a whole bunch of allotropes of carbon. But when we talk about elemental carbon, we generally are, unless otherwise stated, talking about the most common allotrope, which is graphite.